Hello, I'm going to go over the physics exam of November 2022. First question is about Titan. It's one of the moons of Saturn. It has this mass, this radius in km. The average density of this moon gives an impression of the composition of the lunar rock. Calculate the average density. Well, for density we can use the symbol rho. It's just the mass divided by the volume. The mass is given there in kilogram, and the volume of a sphere is 4/3 pi. And then we need to take this radius to the power 3. 2575 times 10 to the power 3 to convert it into meters. And we plug that in the calculator. For 4/3, I just use 1 point. Just keep a bunch of significant figures here. Times pi times the radius to the power 3. Close the parenthesis. Put it in scientific notation. Then how many significant digits I keep? There are 3 here. Yeah, in the American system, okay, this is 4 significant figures. So we can just keep 3. So 1.89 times 10 to the power 3 kg kilogram per meter cubed. Calculate the acceleration due to the gravitational force on the surface of Titan. Well, the acceleration due to gravitational force, there's basically an equation for that you can use immediately. Say G on the surface of Titan is just the gravitational constant times the mass of Titan divided by the radius squared, the radius of Titan squared. And this is, if you have an object with mass m, this is just the gravitational force divided by m, which is the acceleration. So it's independent, as you all should know, independent of the mass of the object being accelerated. So the gravitational constant should be in Venus under Natuurkonstante. Let's keep 4 significant digits here. 4 times 10 to the power minus 11. Then the mass of Saturn, the mass of Titan, we talk about the surface of Titan here. 1.35 times 10 to the power plus 23, of course. And again, we have this radius here, which we need to square. That is, let's just keep 3 significant figures. 1.36 times 10 to the power 0. So this 1.36 then meter per second squared. So quite a bit of a lower acceleration than on the surface of Earth. Titan moves in a circular orbit around Saturn. The radius of this orbit is given here. Calculate the orbital period of Titan around Saturn using the radius of this orbit and the mass of Saturn. Well, the orbital period of Titan will depend on the speed of Titan around Saturn, which on turn depends on the acceleration. So we have the speed of a circular orbit is related to the period by this relation. It's just the distance traveled in one circle divided by the time. Now, the second thing we know about the circular orbit is the relation between speed and acceleration. That's given by acceleration is the velocity squared divided by the radius. And the acceleration in turn can be found by the gravitational force between Saturn and Titan divided by the mass of Titan. So let's combine this first. Let's first get an expression for this acceleration. So here we find that acceleration, this gravitational force, is given by G times M Titan times M Saturn divided by the radius. Again, these both are the radius of the orbit of Titan around Saturn. I have to square this. And then I need to divide by the mass of Titan. So as usual, this acceleration doesn't depend on the mass of the object. So this drops. So this is just G times the mass of Saturn divided by the orbital radius. Okay. And from this you can find the speed, and the speed you can find the period. So let's isolate t from here. So let's get a little bit of space here. T is equal to 2 pi r divided by the speed. And from this follows the speed is the square root of the acceleration times the radius of the orbit. So this is just equal to 2 pi r divided by the square root a times r. And we can just write it as 2 pi times the square root of r divided by a. All right. This is r divided by the square root of r, which is the square root of r. And now I'm going to substitute the expression we have here for acceleration. So it's 2 pi times square root r divided by this thing. So, okay, let me write it out. divided by G, mass Saturn, divided by R squared. So this multiply the numerator denominator by R squared, and you get 2 pi times the square root of R cubed divided by the gravitational constant times the mass of Saturn. All right. Okay, so this requires actually some manipulation of the different relative equations. Okay, so this 2 pi, and now we can just start substituting. First the radius of the orbit in meters, 10 to the power 9, and I need to cube that. Then we have our gravitational constant again. I think I had it here. 6.674 times 10 to the power minus 11. And I need to multiply this by the mass of Saturn. Okay, so maybe it's in Venus. Let's look at here, Sonnenstelsel, which means the solar system. There are some planets here. Okay, here we have Saturn, Saturnus, and the mass is here. It's 568 times 10 to the power 24 kg. And this whole square root we need to extend as well. So let's do first the expression here of the square root. So the radius cubed divided by the gravitational constant and then the mass of Saturn and the square root, and then times 2 times pi. So this is 1.39 times 10 to the power 6. Then the units should be seconds. All right. Then Titan has an atmosphere. To investigate this atmosphere, a soft landing is performed on the Titan. First, a spaceship is put into orbit around Saturn. The orbit of this spaceship and Titan lie in one plane. An observatory on Earth is also located in this plane. The directions of the spaceship and Titan's velocity relative to Earth are indicated in figure 1. The size of the spaceship's velocity is 12.9 here, and Titan is also given here. Then radio waves are constantly being sent to Earth from the spaceship. During the time the spaceship is behind Titan, as seen from Earth, radio waves emitted from the spaceship cannot reach Earth. Calculate the length of time during which these radio waves do not reach the observing station. Assume that the angle at which the spaceship is seen from Earth hardly changes. Okay, so we have Earth here, and then we have Titan moving at a certain velocity. So I've seen as from the reference frame of Earth. So this is V Titan. And then we have a spaceship with a velocity here, 12.9 kilometer per second. And well, so if the spaceship is behind Titan, obviously it will be hidden. And you can actually draw a line here. But actually, since the angle at which the spaceship is seen from Earth hardly changes, and this is really a long distance compared to the radius here of Titan. So these are practically horizontal lines. So for purpose of this calculation, this distance here is just 2 times the radius of Titan. So this has a certain speed, and the component in the y direction, if we call this y, is, let's draw this here a little bit more isolated. So we have an angle of 60 degrees here, and this is phi Titan. So this component here is the sine. Just use from what you learn in calculus about the unit circle, the sine is basically projection on the y-axis. And we get this speed here is the sine of 60 degrees times the speed of Titan. Okay, so they both have a component in the y direction, so it's we to figure out how long this is actually hidden, we need to look at the relative speeds. So the relative speed in this direction is 12.9 minus this component. So phi relative is 12.9 kilometer per second minus the sine 60 degrees times the speed of Titan here. So let's calculate that. 12.9 minus the sine of 60 times 5.6. Right. Times 5.6 and plus 12.9. That's 8.05 kilometer per second. And the distance that has to be traversed is twice the radius. So the time then is, let's say delta t is then twice the radius Titan divided by the relative speed. It's 2 times, what was the radius again? Here, then 2575. Let's keep it in kilometers because the speed is in kilometers per second. So divided by 8.05 is 2 times 2575 divided by 8.05 is 640 times 10 to the power 2 seconds. At a certain point, a space probe leaves the spaceship. After a few days, this probe enters Titan's atmosphere at great velocity. Due to friction with the atmosphere, a lot of heat is generated. This heat is completely absorbed by the heat shield. We have a surface area of 8.7 square meters. At some moment, the velocity of the probe is 0.74 kilometer per second. The frictional force is then 6.0 kilonewtons. Calculate how much heat is developed per second on 1 meter squared of the heat shield at that moment. Okay, so we have our space probe, which is going through the atmosphere with some great velocity, or there will be an opposing friction force. And this friction force performs work on the probe to make it slow down. So negative work. You can see it's pointing in the opposite direction of the velocity. And the work per unit time is given by the power performed by this work, which is an equation that should be known. It's well, I'm not sure if you guys know this in vector format. Let's just put it in scalars. It's the force times the velocity. And one of these actually has a negative sign, given that it's pointing in the left direction. This is negative, this is positive. But we here don't care about it. We just calculate this. This is the power that goes into the heating of the shield. And per square meter, so what they're actually asking is what it is per unit area. So let's call this lowercase p. Is this capital P divided by the area? So it is the force of friction times the velocity of the probe divided by the area of the shield. Okay, I could have. Okay, now let me substitute them here. 6.0 times 10 to the power 3 times 0.74 times 10 to the power 3 meters per second divided by 8.7 meters squared. Six. And that is 5.1. How many figures shall we keep? 2 figures. Since the velocity is given in 2 significant figures. So times 10 to the power 5 meter. No, not wait. Yeah, so this unit is watt per square meters. Or watt per square meter. Okay. When the velocity of the probe has slowed down enough, the heat shield will be thrown off. Moments later, a parachute opens, further reducing velocity. The probe now descends vertically. Figure 2 shows the height above the surface of Titan against the time since the parachute opened. So here I have a graph with height and time, and all the motion is in the vertical direction. At the height at which the parachute opens, the acceleration due to the gravitational force is 1.18 meters per second squared. At that altitude, the deceleration of the probe is 0.89 meter per second squared. The probe with parachute has a mass of 192.3 kilogram. Calculate the magnitude of the frictional force on the probe and the parachute assembly at the height at which the parachute has just opened. So at this height, the probe is actually decelerating. So let's draw that. It is a acceleration in the positive direction. Let's define the surface of Titan as going into the negative direction. It's decelerating, so we have this, and it is given 0.89 meter per second. And acceleration due to gravitational force is 1.18 at that height, so that's a little bit larger in magnitude, 1.81 meter per second squared, of course. So there is a net acceleration of 0.89. So a net or resultant, or however you want to call it, 0.89 meter per second squared. The acceleration due to gravity, or let's just call it G. It's 1.81 meter per second squared. So the difference is coming from the total friction of the probe and the parachute. So what is this acceleration due to friction? Well, we know the net acceleration and we know the acceleration due to gravity. So we know the net acceleration should be the g plus the acceleration due to friction. In other words, the acceleration due to friction is the net acceleration minus the acceleration due to gravity. And this is 0.89. And the gravity is in the negative direction, so minus negative 1.18. And again, be very careful with signs here. So this is what is it, 207, no space here, meter per second squared. I just need to add these two numbers here. So this must be the one coming from friction, and together with the acceleration from gravity downwards, it leads to this net acceleration. But what are they actually asking? Okay, what does it mean for the magnitude of frictional force? Well, that means that the force is the mass times acceleration. So the friction force is the mass of the probe times the acceleration, which we have here, which is 9.3 times 2.07 is 3.98 newtons. Probably should give it in two significant figures, but I'm sure they will count this correct, except that it's uh, okay. Here, 3.98 Newton. Determine the velocity at which the probe finally lands on Titan. Well, where it lands on Titan is where the height is 0. So let's grab this and see. This is height versus time. So it's displacement over time. And what we know is that the slope of displacement over time is the velocity. So we just need to figure out what the slope is from here at this point. So we just need to try to draw a line here. It's actually not that straightforward. So there's actually quite some margin of error in this. But it's a little bit easier to do on paper, in your exam paper. But just draw this line, and I don't really have the hang of it in Jamboard here. Okay, so, and then take the furthest point possible. So we have slope equals delta y divided by delta x. Zero, the y here is 0, minus, and here there are 10 subunits for 20. So each minor unit here is actually 2. So here we have 1, 2. So this is 44. And then here we just have 4 hours, which is 4 times 3600 seconds. And here we need to multiply, let's just give the velocity in meters per second. So 44 times 10 to the power 3. And you can see it has a negative sign of, since the goes in the negative direction. 44. So this is 3. And I wouldn't even take some more than 2 significant digits, actually, times 10 to the power 0. So 3.1 meters per second. Okay, so that is completing question 1 then. Question 2 about the rotator spring. A rotator spring consists of a spring from which a cylindrical mass hangs. The mass of the spring is suspended from the ceiling. The combination is shown in figure 1. When the mass is pulled vertically downwards and then released, a special movement is observed. At first, the mass moves vertically up and down and hardly rotates. Then the rotation increases and the up and down movement decreases. Means that some energy is transferred in the rotational movement. After a while, the mass just rotates and the vertical movement disappears. Then the vertical movement slowly starts again and the rotation decreases until the mass only moves up and down and no longer rotates. This is repeated until the mass comes to a standstill due to damping. The mass of the cylindrical mass is 2.8 kilogram. The spring constant is equal to 49 Newton per meter. To demonstrate the movement, the mass on the spring is gently pulled down 8 centimeters, but not yet released. Calculate the force of the spring acting on the mass. Give the answer with the correct significance. Let's draw the free body diagram of the mass here. So we have a gravitational force acting downwards, which is given by the mass times g, and it's also pulled down by 0.08 meters. So we have an applied force, which is, well, whatever this extension is, times the spring constant. So the extension is a function of the extension is exactly linear in the force given by this linearity constant k, the spring constant. And then in order for this to be in rest, we need to have like a counter spring force going up here. So this has to be the absolute value of this, and let's define these number all as positive. And we need to have this to be equal to Fg plus the applied force. So we simply find the spring force acting on the mass to be equal to 2.8 times 9.81 plus 0.08 times the spring constant. That is, we need to have the correct number of significant digits. Like, well, we see the spring constant as well as the mass is given in 2 digits, so we'll keep 2 times 10 to the power 1 Newton. Okay, that's also what they found. The mass is pulled down a little further. When the mass is released, the spring moves up and down at a frequency of 0.67 Hertz. Demonstrate this using a calculation. Okay, for this we need to find or remember the equation of a harmonic motion due to in a spring mass system. And I think that might be given in Venus. It's still so important that you should remember it. Let's go to the section of physics formula. Here it's under veerkracht, so spring is a veer in Dutch. And oh wait, no, this is not actually. We need to look at oscillations, frequency. Okay, here a mass spring system. So this is the equation we need to use here. So the period is 2 pi times the square root of the mass divided by the spring constant, which are called K. All right, so that's just substitution then. So it's 2 pi times 2.8 divided by 49 and then the square root. So that is 1.5. Let's keep some more digit in the intermediate calculation. 2 seconds. That means the frequency. Well, I can just take this intermediate number and do the inverse. Where is that again? It's 1.5 seconds. So that's 6.7 times 10 to the power minus 1 Hertz. Okay. The distance h from the center of the mass to the floor is shown as a function of time on answer sheet in figure 2. Use figure 2 on answer sheet. Using it, determine the distance from the center of the mass to the floor when the mass has come to rest. Okay. So mass has come to rest. Okay, well, where is that happening? Well, the height of the floor is given here, so it's just we just put a horizontal line here. And oops. Okay, so that's not super simple in Jamboard. Here, so this is 0.85, and they divided this in 1, 2, 3, 4, 5 minor grid units. So it is about 0.87 meters above the ground. In figure 2, an answer sheet indicate with the letter V all moments at which the mass moves vertically up and down and does not rotate. Let's see if I still have it. Yeah. So it moves vertically up and down and no, does not rotate at all. So that means all the energy is in the vertical movement. And that means the deviation, that's at the points where the deviation from the equilibrium position is the largest. So that is happening here, 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 here. Okay. Then the angle alpha over which this mass rotates as a function of time is measured. The result of this measurement is displayed in figure 3 on the answer sheet. Use this answer sheet to determine the rotational frequency of the pendulum as accurately as possible. Justify your answer. Give the answer with the correct significance. So let's look at figure 3 here. Okay, so here we see the deviation from the equilibrium as function of time. And in order to figure out the period, which is the peak-to-peak distance here, the best we can do is just go to the peaks to the far left and far right and find out what the associated times of these are. So let's try to do that. I drop a line here. I drop a line here. It's not so easy to do on a writing pad. I'm kind of off here. Let me just see if I can do it a little bit better. Okay, and then we find this is one grid unit is exactly 1 second. So this is about 10.1. And this is 45, 46, 47, 47.6. Now, what is the accuracy here? Besides the fact that I'm using a writing pad, I would argue it could be plus or minus 0.2 seconds on both sides. So let's just assume that. It might be actually 0.1 if we can do this a little bit better. And now we need to count how many peaks this is. So this is one period, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 20. 1, 2, 3, 4, 5. So these are 25 periods. So then you can conclude that the period T is 47.6 plus or minus 0.2 minus 10.1 plus or minus 0.2 divided by 25. Okay, I don't actually need a calculator for this, but that is 37.5. Okay, I do a cut here. I do a cut. I do a cut. 47.6 minus 10.1 divided by 25. And this is kind of an integer number of waves, so there's no error in this. Look at 1.5, and let's just keep 2 more significant digits, but we'll analyze that. Then I can just assume what, in the worst case scenario, you get plus 0.4 from these two, or minus 0.4, so plus or minus 0.4 seconds, which we have to divide by 25. So you get a plus or minus 0.016 seconds. Now, what kind of percentage is this of 1.5? So it's about, so that's 1%. That means 1 in 100. So we can write this in terms of significant figures as 1.50, with this last digit being uncertain. So T is 1.50. That means that the frequency is then just 1 divided that. That means 0.667 hertz. And I again keep 3 significant figures here. Question 3 about a long wire. A long strand of insulated copper wire is wound into a coil. Later one wants to determine the length L of the wire. The coil must not be unwound. The coil has 2 terminals. See figure 1. One can determine the resistance of the wire and use this to calculate the length of the wire. One has a DC voltage source. One has a DC voltage source and a current meter and a voltage meter. With this, one can make a circuit to determine the resistance. Draw this current using the appropriate symbols. So what are the appropriate symbols? Well, we have our peanuts here. Go to the section about electrotechnique, and there is a table about symbols to use. Okay, so we have a coil. Where is the coil? With or without a core. I think this one is without a core, as far as I can just remember, but doesn't matter. We can always put just a line on top of it. Okay, so let's draw the coil, and we have a ampere meter, so we can put this anywhere in the circuit. It's just a circle like this, and we have a voltage source. Okay, then the voltmeter is always put in parallel. They have a high resistance, so we put this here, and with this we can measure the voltage across the coil. That was 3A. I'm actually not sure about this. I think if you use the kind of common symbol like this, it's fine as well. The voltage meter reads 0.56 volt and the current meter 0.23 amperes. The diameter of the copper wire is 1.5 millimeter. Calculate the length L of the copper wire. Well, the resistance of the coil is then just V divided by I, the voltage over the current. And that's then 0.56 divided by 0.23 is 2.435 ohm. And they give the diameter. Now, what we want to use is that the resistance of a wire is given by the resistivity times the length. That is actually a lowercase l divided by the area. And we know this. We know the area from diameter, and did they give the... Okay, I guess we have to figure out what the resistivity of copper is. So go back to our BNOS. Figure out what is the resistivity of copper. So let's go to metals. So copper is koper in Dutch. En resistivity is soortelijke weerstand. En copper is the low one here, 17. See, copper has one of the lowest resistivities. That's why it's used so often. The rho of copper is 17 times 10 to the power 19 ohm meter. Okay, so how do we figure out L? Well, L is just equal to the resistance times the area divided by rho. And that's the resistance times, well, what is the area? The area of a circle is pi r squared. But now we know the diameter, so that's, see, 1/4 pi diameter squared. Just substitute that r is half the diameter. So I get this divided by rho, but this is just pi r d squared divided by 4 times rho. Now I can just substitute everything I know. The resistance given here. The diameter is 1.5 times 10 to the power minus 3. And then I need to square this and divide it by 4 times 17 times 10 to the power minus. Wait, this was not a 19. Yeah, 9, of course. 10 to the power minus 9. So we put this in the calculator. We get pi times 2.435 ohm for the resistance. And then 1.5 times 10 to the power minus 3 squared. And I need to divide that by 4 and divide it by 17 times 10 to the power minus 9. And this is 250. Let's put it in scientific notation with the two significant figures. So that's 2.5 times 10 to the power 2 meter. One can also measure the magnetic field strength of the coil and calculate the wire length using that. The circuit of meso 1 is then used, and a magnetic field sensor is placed in the middle of the coil. 8 times the magnetic field strength B is measured as a function of the current length L. The measurements are shown in the graph figure 2. In the BINAS data book, there is a formula for the magnitude of the magnetic field in a coil, given here. This is one of the formula you should have learned talking about magnetism. Based on this formula and the measurements, a straight line has been drawn through the origin with slope 5.81 millitesla per ampere. Okay. Explain why a straight line was drawn. Well, obviously B B is proportional. I have in a direct, I think you call it direct relation to I. So if you want to find this constant in front of I, you would draw a straight line. Okay. C1, C2. Explain why this line was drawn through the origin. Well, if I reaches 0, then V equals 0 according to the knowledge here. So it will go through the origin. Explain why the slope is 5.81 millitesla per ampere. Actually, I'm not sure what I mean here. This number, of course, depends on the different constants here, like the permeability, T length, and N. So I'm not sure how to explain that this is 5.81 millitesla per ampere. The slope of this line basically gives this constant in front. But otherwise, I don't think this question is really that clear. So yeah, again, B is basically some constant times I. And this is the slope. Calculate the wire length L using the extensor formula. Well, we know that this slope here gives us the constant in front of I. So we know mu 0 n times the square root of L squared plus D squared is equal to 5.81 millitesla divided by ampere. So times 10 to the power minus 3. So n is just given by that number times the square root of L squared plus D squared divided by mu 0. And now we can just substitute L equals 0.2, E is 0.08 meter. Why did I put a 0 here? Mu 0 is given here, what's given here on top. So we know everything. We just substitute this. So first do the square root, 0.2 squared plus, not times, and divided by the permeability of vacuum, 1.257. I keep 4 significant digits. And then multiply this by that slope. Then I get 996 approximately turns. I have these loops in the foil. Now we know the diameter, so we know the circumference of one loop. So circumference, one loop is 2 pi r, which is 2 pi times the diameter divided by 2 is pi times the diameter. Pi times the diameter 0.08. So that's 0.2513 meter. And I just need to multiply this by the number of turns. Then I will get the total wire length. So times 996. So then I get L is the N times the pi times D is roughly 250 meter. Explain whether the formula for peanuts will lead to a larger or smaller wire length for this coil compared to the more extensive formula. Well, n is, as we just saw, n is proportional to this square root, L squared plus D squared. So in this peanuts, we ignore D. So n will be smaller than the length estimation will be smaller too. Moving on to question 4. There is a gas in a container. This is shown schematically in the figure. The container consists of 2 cylindrical parts, an upper part and a lower part. It's closed with a piston here that kind of can freely move without friction. And there is a valve A, which is closed. The volume of the piece of pipe between volume 2 and the valve may be neglected. Calculate the height h2. So that's the height of volume 2. Well, the volume 2 is equal to the height 2 times the cross-sectional area, say area 2. So the height 2 will simply be then the volume 2 divided by the area 2. Which is 0.015 meter cubed divided by 0.075 meter squared. So this is 0.2 meter. That's correct. with the piston Z in the upper position, as in the figure, the pressure PA in the vessel is given here, and the temperature given here. We call it T sub A. The pressure of the outside air is this. Calculate the mass of the piston. So if I just draw the piston, and there is from the top the pressure of the outside air, which is given here to how many? Five significant digits total. 10 to the power 5. And there will be a weight. The weight of the piston will exert a pressure. So there is, say, a weight W here, which is the mass times the mass of the piston times the acceleration of gravity. And then this all is countered by the pressure of what is actually inside the gas in the container, which is given here, 1.0050 times 10 to the power 5. And we should say we should say the pressure, which is actually the weight per unit area. So I would just actually call this, say, the pressure exerted by the piston, so which is the weight, and divided by the area of the piston. Let's call that a P. So since this is balanced, the piston is not moving, we need to have that this pressure coming from the piston plus the outside air pressure has to be equal to the pressure inside the container so let me see, I can just plug this in and find an expression for M. But let's first just calculate what PT is. So let PT then has to be, I need to subtract these. So this should be what, have one additional zero here. So 0.0050 times 10 to the power 5 Pascal. So then we finally conclude that the mass is the area of the piston divided by the gravitational constant times this number here. And the area of the piston is the cross-sectional area here. So that's in square meters, 0.1. And here we take 9.81. And again, this number here Now I can calculate it. 0.1 times 0.005 times 10 to the power 5 divided by the gravitational constant. That is 5. Let's see how many we want to keep. It's generally 3 significant digits. So say 5.10 times, not times, 5.10 kilograms. Okay, they kept 1 significant digit. Yeah, probably that's good. That's well, you're subtracting like 2 F large numbers here. So in the end, it probably makes sense to keep only 1 here. Anyway, as far as I understand, it's not a big deal if you know, except if they specifically ask for the number of significant figures. Now we cool it to a temperature TB of 360 Kelvin. Show that the piston just touches the upper edge of the lower cylinder. Okay, so we start with a pressure P capital A and temperature T capital A. And we change the temperature by cooling it. So what we just use is the ideal gas law, which tells us that the initial pressure, so that's PA times the volume A divided by the temperature A, has to be equal to the pressure B, the situation B. Now, in this case, since the piston is free to move and the weight and the outside pressure actually remain the same, we should ignore this small height here. We can just assume that PB is equal to PA, the pressure is the same. Well, the temperature change, that's given, and volume will change as a result. This is one of the other gas laws, but you can just start with this ideal gas law and figure it out. So we get the volume in state B is just equal to temperature in state B divided by the initial temperature times the volume A. And the temperature, what was the initially the temperature was 327 degrees Celsius. So that was in Kelvin, that's this. And we cooled it down to 360 in Kelvin. And the volume, the total volume here is the sum of these volumes, which is 0.025 meters cubed. So let's calculate this. We get 0.0417 meters cubed. And all right, so that's the volume. So the height well, this is actually should be equal to the volume in 2. So why does this? Ah, I have it completely wrong. I messed it up. Of course, the volume should go down. This is okay. Oops. So let's go to show, double check everything, and work slowly. The final temperature is cooled down to 360, so TB. And the initial temperature was what I wrote down, 273 plus 327. Okay. 360 divided by 273 plus 327 times 0.025. This is 0.15 meters cubed. And this is equal to the volume 2 here. So the piston is just touching the upper edge of this lower volume 2. The gas is then further cooled to TC 27 degrees Celsius. Calculate the pressure of the gas. Okay. So the ideal gas law then says that the pressure in state C times the volume in state C divided by the temperature in C has to be equal to the pressure in state B times the volume in state B divided by the temperature in state B. Now in this case, since the piston cannot move down any further, the volume remains constant. So I can just say Vc equals Vb. So from this, we find that the pressure in state C is the temperature in state C divided by the temperature in state B times the pressure in state B. And this also is all known. The temperature in state C is 27. And let's do it correctly now. And the temperature in state B was 360. The pressure in state B is still the same pressure we started with, 1.0050 times 10 to the power 5 Pascal. So we get 8.38 times 10 to the power 4 Pascal. So it's reduced by quite a bit. Now the valve is opened and gas at 27 degrees Celsius flows into the vessel via valve K until the piston returns to its upper position. Let's see the figure. Calculate how many moles of gas of 27 degrees float into the cylinder via valve K. So the knowledge here we need to apply is that the number of moles of gas in a volume can be found through P times V divided by T is the number of moles times the gas constant R. So obviously through this whole process, the number of moles of gas didn't change. So we can just check in this final state and in the initial state what the number of moles is contained, and then the difference is how many moles has flowed in. And for the initial state before the valve opened, we can use either state A, state B, or state C. Actually, let's just take state A, since all the information is here. It doesn't matter. So let's just take state A. So we have number of moles in state A will then be equal to pressure A VA divided by R TA. And the pressure was given there. The volume is known. R is to be found in Venus 8.314. And the temperature A is Well, it was actually says 600 Kelvin. This was the initial state, so we just find out what this is. No. Let's keep these temperatures are with 3 significant digits, so let's just keep, doesn't make sense to keep more. So we get 5.04 times 10 to the power minus 1 mole. And then finally, that's what we call D. The pressure in this final state is exactly the same. The atmosphere and the piston put the same amount of pressure as before. It returns to exactly the same state. That's a given here. So that is also the same as the initial. The volume is also the same. So as a matter of fact, the only difference is the temperature, which is 27 Celsius, so it is 300 Kelvin. Now, at a lower temperature, more moles of material actually fit in. Just at the same pressure and the same volume. Let's see then how much this is. And this is 1.01 times, oh, this is 1.01 mole. So then we have finally 1.01, and initially we had 0.504. Because of the error, I don't even need to care about this digit, so subtract these 0.51 mole flowed in. Now we move to nuclear power. In the reactor inside the reactor building of a nuclear power plant, heat is released by nuclear fission. The heat is transferred to the water in the primary cooling circuit. That's the cooling circuit given here. The heat is transferred via a heat exchanger to the secondary cooling circuit, which also contains the turbine that drives the generator. So heat is exchanged here, and this secondary circuit drives the turbine. Nuclear fission also releases neutrons. This irradiates the water in the primary cooling circuit that flows through the reactor. When a neutron strikes the oxygen nucleus in a water molecule, a nitrogen 16 nucleus N16 is formed. This reaction releases another particle below the reaction equation where 6 places still have to be filled in. Okay, so it is in this area here where these nitrogen-16 nuclei are formed. Write down the reaction equation and complete it. Well, we have 16 oxygen, so mass number 16, so 8 protons, 8 neutrons. Well, it captures a neutron, so neutron has a mass number of 1 and 0 protons, obviously. And they say it's nitrogens, so nitrogen, okay, I happen to know that, remember that, has 7 protons. You can look it up. That means that we need to have something with a number of protons of 1 and total mass number of 1. Well, what is that? That can only be a proton or a hydrogen nucleus. Then this N16 is taken along the primary cooling circuit. In our mind, we follow a liter of water as it goes through the primary cooling circuit. The number of N16 in this liter of water varies as it goes around. This is shown in figure 2. At A, the water enters the reactor core every time. At B, it goes out. A and B here. Locations A and B are also indicated in figure 2. We assume that the nuclear power plant is in continuous operation for a year. A liter of water contains so many water molecules. A small percentage of the water molecules originally present in 1 liter of water is affected in that 1 year. Let's see how many molecules are affected. You can see that the oxygen in the water molecules, some of these will change in this nitrogen 16. In 1 liter you have, well, some number that's given here, and then it goes up because the capture by the neutrons, and then apparently they go down again. They decay back into, this nitrogen decay back into oxygen. So, well, it's given here how many actually are affected in 1 cycle. In 1 cycle, let's make it 3.2 times 10 to the power 10 minus, this will be 0.9 times 10 to the power 10 equals 2.3 times 10 to the power 10 are affected. Now, a water molecule, H2O, has 1 oxygen atom, right? So that means also so many water molecules. No, are affected in a cycle. In a cycle. And a cycle, the cycle time is, well, uh, let's start at 0 here and see when it's back at 0. So this is 1 cycle, another cycle, and this is about 30. And these are 2 cycles, so cycle time is 30 divided by 2 is 15 seconds. So how many times 15 seconds are there in a year? So per year, we need to calculate the number of seconds in a year, which is 365 times 24 hours times 3,600 seconds, and divided by 15. This is 2.1 times 10 to the power 6 cycles. So therefore, 2.3 times 10 to the power 10 times 2.1 times 10 to the power 6 molecules are affected. And this is equal to 2.3 4.8 times 10 to the power 16 molecules per liter. And as a percentage out of space here, as a percentage, that's then 4.8 times 10 to the power 16 divided by 3.45 times 10 to the power 25. That's actually a very small percentage times that ratio times 100% is 1.4 times 10 to the power minus 7%. N16 is unstable and decays, emitting beta and gamma radiation. The emitted gamma photon has a very high energy, namely 6.1 MeV. There are special detectors that measure only these high energy gamma photons. With these, the presence of N16 can be determined. We discuss 2 applications of N16. A first application is measuring the velocity of the cooling water flowing in the primary circuit. Detector is placed at 2 locations along the pipe through which water flows. The detector measures high energy gamma photons in an identical manner. Figure 3 shows the measurement results of both detectors. The distance between the detectors is 15 meters. Determine the velocity of the water in the pipe. The radioactivity at detector 2 is much lower than at detector 1. And that's because in the time the water traveled from 1 to 2, a bunch of these already decayed. So let's look at this ratio of the radioactivities at detector 2 and 1. That is 6.2 and about 7.9. I don't need the 1000 here because they will be in both here and they will drop. So this is 0.78. That's the ratio. Now, we also know that the radioactivity is proportional to the number of radioactive. I think people just use active, not radio in front of it anymore, but okay. Radioactive nuclei. say the N16 nuclei. So we just need to look at what is the number of radioactive nuclei at the second detector compared to the first. Well, that would just be the number at the first detector times 2 to the power minus whatever the time passed in traveling, divided by the half time, T1 half. So we can say that A2 divided by A1 is N2 divided by N1, because they're proportional, is then just equal at 2 to the power minus delta T divided by T 1/2. And we also know that this has to be equal to 0.78. 0.78 equals 2 to the power minus delta T 1/2. Well, we just take the logarithm on both sides, and we get log 0.78 equals the logarithm of, okay, wait, let me immediately simplify it. Minus delta T divided by T 1/2 times log 2. So delta T is T 1/2 the log. I divide both sides by log 2, or there should be a negative sign here. Negative sign. Okay. Just out of space a little bit. T 1/2 log 0.78 divided by 2. So it's 0.41 times T 1/2. Now we just need to figure out what is the halftime of this. So let's see in the peanuts. There is a section about radioactivity. Isotopes. Where is it now? I'm a little bit out of space, but I want to keep this. I just continue here. T 1/2 is actually 7.13 seconds. Okay. So delta T equals 2.9 seconds. And then we can figure out the velocity. Okay. V is then 15 divided by 2.9. No, I did that wrong. is 5.2 meter per second. And they have 4.9. I guess that must be coming from these activity readings here. A second application is leak detection. In figure 1, the letter X indicates a location close to the secondary cooling circuit outside the reactor building. There's the detector there. In normal operation, this detector does not measure high-energy gamma photons. If detector X nevertheless registers high-energy gamma photons, it's immediately clear there's a leak somewhere. Explain where the leak is and indicate this in the figure on the answer sheet. All right, here it is. So there is a leak here, or there not a leak there. The gamma rays, the high energy gamma rays, are detected here at X. So that means there must be some of the nitrogen-16 decaying there into gamma rays. So where are these generated? Well, they're generated here in the cooling circuit. So yeah, that means that in this like heat exchange thing here, there must be some leak. Some of the water from the primary circuit flows over into the secondary circuit. So in the heat exchange, between the primary and secondary circuit,